Okay, so today's video we're going to be talking about something called the fast-growing hierarchy. And the last thing we visited before was Graham's number, but in order to go further, we're actually going to have to go back to basics here. So I'm going to explain a very, very simple function with very, very far-reaching applications. So the fast-growing hierarchy is denoted as f, and there's a number in the subscript and an input to the function. And this is going to equal some output here. So the first function in the fast-growing hierarchy we deal with is something called f sub 0 of n. So this is the first index of the fast-growing hierarchy, basically. And this is a very, very simple function, basically. All this equals is, f sub 0 of n is simply equal to n plus 1. So this is called the successor of n. It's an operation that's even more simple than addition. It's called successorship. So to do an example, very simply, f sub 0 of 3 is equal to 3 plus 1 is equal to 4. So very, very simple. From here on, the fast-growing hierarchy follows a general formula. And I'll write that up here. So f sub a of n is equal to f, or n copies of f, a minus 1 of n. So to make this clear, I'll do another example here. Let's take f sub 1 of 3. The next simplest index is obviously 1 after 0, so we'll do that. F sub 1 of 3. So let's break this apart, basically. In this case, n is 3, so we're going to go 3 copies of the f 0th function, because in this case a is equal to 1, so we're going to have to take 1 minus 1, which is equal to 0. And this is going to be of n, which in this case is 3, so we'll put a 3 here. Now another way of writing this out, basically this superscript here, 3, means 3 copies of the f0 function. So we're going to take f0 of f0 of f0 of 3. That's another way of writing this out, kind of a nested functions, basically. And of course, the order of operation is fairly obvious here. We do the inside of the brackets first, and we work our way out. So what's f sub 0 of 3? Well, we already did this. It's simply the successor of 3, which is equal to 4. So let's just put a little 4 up here, just so we know where we are. Now this 4 is inside the brackets of this one here. So now we take f sub 0 of 4, which is 4 plus 1, which is going to equal to 5. F sub 0 of 5 is equal to 6. So this is going to equal 6. Now if we took f sub 1 of 5, the same kind of thing. In this case, n is equal to 5, so we do 5 copies of the 0th function of, in this case, 5. And it's the same kind of thing. So we have 1, 2, 3, 4, 5, and a bunch of brackets here. And the same thing. So we take f sub 0 of 5, which is equal to 6. We go 7, 8, 9, 10. So we can kind of see what's happening here. Basically what the f1 function does is it takes the number and it doubles it. So let's basically just write down a generalized formula for the f1 function. So f1 of just a general n is equal to 2n. Okay. So with that, let's move on to the f2 function this time. So f2 of, let's say, 3. We're going to go back to our equation here. So in this case, n is 3 again. So we're going to have 3 copies. A is 2. So we're going to go 2 minus 1, which is 1. And this whole thing is of n, which is 3, so 3. Rewrite that as f1 of f1 of f1 of 3. Now we're going to use our formula here to figure this out, because otherwise we have to expand this out in terms of f0 or whatever, and it's going to get really long and messy or whatever. So we're going to use our general form right here, so 2m. So f1 of 3, double 3 is equal to 6. f1 of 6, double 6 is going to be 12. Double 12 is going to be, finally, 24. So this equals 24. So in this case, what the f2 function is doing is it's doubling the number n number of times, which n in this case would be 3 or whatever. So there's another formula we can write down for the f2 function in general of n. It's going to be 2 to the power of n times n. And that basically just means we're taking the original number here and we're doubling it in number of times. So that's a way of writing down f2 in just a general form or whatever. So let's try to make slightly larger numbers. Let's go with the f3 function and try to write it down in terms of this here. So let's take f3 of 3, and we'll just see how big that number is. So f3 of 3, same kind of thing. We take 3 copies again. So I'm just trying to keep this formula visible so you guys know what I'm doing here. So n is 3 again, so 3 copies. This time a is equal to 3. 3 minus 2, or sorry, 3 minus 1 here is equal to 2 of 3. So write that down, expand it a little bit. f2 of f2 of f2 of 3. Okay, so f2 of 3. Let's just write that down in this form right here without expanding it out. So I'll start over here a little bit. Okay, so f2 of 3, we know, is equal to 2, and n is equal to 3. So we're going to do 2 to the power of 3 times 3. So that's what this is going to equal here. So now we're going to take f to the 2, or sorry, f sub 2 of 2 to the power of 3 times 3. So now n is going to equal our 2 to the power of 3 times 3. So that's going to equal 2 to the power of, in this case, n is going to be this whole thing right here. So 2 to the power of 2 to the power of 3 times 3 times n, which is this also, 2 to the power of 3 times 3. That's going to be this part right here. And we still have one f sub 2 function we have to do to that. So f sub 2 of this here, I'm just going to put an arrow saying, I don't want to write that out again, of that is going to equal 2 to the power of this whole thing right here. So we'll just write that 2, 3 times 3 times 2 to the power of 3 times 3 times this whole thing again, because that's what we is defined as n, times 3 times 3 times 2 to the power of 3 times 3. So it gets a little tedious to write out, but I wanted to write this out just to show you that the fast-growing hierarchy, even though it starts very small, very humbly, just adding 1 to a number, this recursive definition of it is where the power comes from, and we actually get quite large numbers. So if we work this out a little bit, 2 to the power of 3 is 8 times 3 is equal to 24 or whatever. So we can write this out a little bit more simply. Let's turn all these 2 to the power of 3 times 3s into 24. So we actually have 2 to the power of 2, power 24 times 24 times 2 to the 24 times 24. Okay, now using our logarithms, I won't do this explicitly, but you can do it if you're so inclined or whatever. We can turn these 2 to the powers into base 10 or whatever, just because base 10 is something most people are used to using. So I like to have everything in base 10 if I can do it. So this turns into 2 to the power of 10 to the power of 8.6 times 10 to the power of 8.6. And because of and then basically this right here, we can turn this into another base 10 or whatever. So this ends up being 10 to the power of 10 to the power of 8.1. So basically we did that, remember that rule before where we did log 10 of 2 ends up being like negative 0.5. So we just minus 0.5 from here, and we can turn this all into base 10. And this is times 10 to the 8.6. Now what's happening here, basically, we can do a little rule of exponents here. So we can actually write this out as 10 to the power of 10 to the power of 8.1 plus 8.6. So if we have a multiplication and these bases are the same, basically we could just add this number to this part right here. Now 10 to the 8.1 is a fairly large number in the 100 millions. If I add 8.6 to 100 million, it's hardly going to do anything to it. So for all intents and purposes, this is roughly equal to 10 to the power of 10 to the power of 8.1. So this is a fairly substantial number. It's much, much larger than a Google. It's not quite as large as a Googleplex, which is 10 to the 10 to the 100. But already, like, it's getting fairly sizable. And this is only for f sub 3 of 3. If I were to go f sub 3 of 4, this would be on the order of 10 to the power of 10 to the power of 10 to the power of like 20.5. So this is already way, way, way larger than a googolplex, and it goes on from there. F sub 3 of 5 would be a tower of like 4 tens with this same number on top, 20.5, something like that. So, and that's just adding a number to this element right here. We haven't even raised the 3 yet. We're still just on the 3s. So as we can see, we see something a little bit familiar here. The F3 function is very similar to tetration, that operation that created towers of exponentials. And what we find in general is that the fast-growing hierarchy, it keeps pace with Knuth up arrow notation. So if we were to have Fa of n, this is similar to 2 with A up arrows n. And mind you, that this isn't a great approximation when you first start out with like F1, F2, F3 and stuff like that. There's quite a large discrepancy. But when you get further up into the A's, like F sub 100 of a number, this would be a fairly accurate approximation, going 2 with 100 up arrows n, which would be a very, very large number, because we remember dealing with numbers even like 3 quadruple up arrow 3, which is with like nested power towers and stuff like that, a very, very large number. And again, even though this is a 2, this number matters least in making large numbers. Basically, this still makes very, very large numbers, and for all intents and purposes, I could change this to a 3, and it really wouldn't change anything, for the exact same reason that we can switch these power towers from like 2 to 10, and it really has no effect on here or whatever. So it's the same kind of principle, basically. This part of the arrow notation has really nothing to do with the size of the number. This matters the least. This matters still not that much, but a little bit more. And then this is the main thing. The number of arrows is the main power of the operation. So just keep that in mind. So don't worry that these are just 2s. They still make astronomically large numbers. Okay, so in the next video, I'm going to be talking a bit about infinite ordinals, but I think that's good for now. Slight a basis on fast-growing hierarchy.